This lecture is on chapter 3.2 and chapter 3.4 on ionic radius and ionic solids and naming. So let's recall back to our periodic trends for atomic radius. So remember, we have our general trends here. As we go from left to the right on the periodic table, we see our radius decrease. And as we go from top to the bottom, we can see our radius increase. So take a moment for just a second. I'd pause the video and determine for yourself why these trends exist. Those are very important concepts. So these trends exist due to two separate reasonings. So the reason that the radius decreases as we go from left to the right on the periodic table is because of a constant increase in the effective nuclear charge as we go from the left to the right on our table. Okay, and whereas the increase in the radius as we go from the top of the table down to the bottom is because we are increasing our overall energy levels, and each of those larger energy level orbitals are extend further away from the nucleus. So these were our periodic trends for atomic radius. Okay, so not ions, just regular atoms. So now how does turning a molecule in or an atom into an ion, how does that affect the radius? So here we show a schematic here showing the atomic radius versus the ionic radius. So the ions are colored red or blue for cations and anions respectively, and then the parent atoms are in brown. And so the radii that are presented to you are in picometers. So take a moment for just a second to pause the video and observe the trends that you see and see if you can uh, develop for yourself the trends for cations versus anions. Okay, so we see here by looking at the data that cations become smaller, whereas anions become larger. And so how can we explain these trends? So the loss of an electron to form a cation in order to form that noble gas configuration increases the effective nuclear charge. So whether we're talking about our alkali metals, which are going to be changing our effective nuclear charge from +1 to a +8 when we get to noble gas configuration, or the alkaline earth metals going from a +2 effective nuclear charge to a +8, or the aluminum group from a +3 to a +8. When we increase that effective nuclear charge, that has the effect of pulling those electrons closer to the nucleus. So there's a stronger attraction to the valence electrons by the nucleus. The second factor, which leads to a decrease in radius for cations, is that we're actually decreasing the overall energy level of our valence shell. So we go from for lithium being a 2s orbital down to a 1s orbital. For sodium, we go from a 3s orbital down to a 2s, or sorry, to a 2p orbital. For potassium, we go from a 4s orbital down to a 3p orbital. Okay, so that decreasing the overall energy level causes a contraction of the overall ionic radius as well. So the increase in the radius that we observe for the anions is because we are increasing the total number of electrons, which has the effect of increasing the electron-electron repulsion within that valence shell. And so that increase in electron-electron repulsion has the effect of increasing the overall atomic radius for our anions. There's no change in the effective nuclear charge on forming an anion, but it's all about this electron-electron repulsion. Okay, and so as we take a look at the effect of forming a +1 cation versus a +2 cation, what we can see here is the larger number of electrons that are removed results in a smaller ionic radius. Okay, so when we see the change from going from lithium to lithium cation, as compared to beryllium to the beryllium cation, you can see that that ion, the 2 plus ion, becomes much smaller. So the larger the charge on a molecule, or a larger the charge on a cation, the smaller the ion is likely to be. And when we're taking a look at our anions here, we can just look to see that in all the different cases here, when we form an anion, we are increasing the ionic radius. So if I ask you the question, which of the following spheres represents the potassium cation, which is the potassium atom, and which one of these would be the chloride uh, minus ion? So I would pause the video and try to reason that through for yourself. Okay. All right. So the first one that we're going to take, so the answer here is the far left is going to be our potassium. The green in the middle is going to be our potassium cation. And the far right, the red, is going to be our chloride anion. So what's going to be our reasoning for that? So our reasoning is our, our potassium versus the potassium cation. We know that cations are smaller than their uh, uh, cations are smaller than their atom cohort. So when we're comparing our potassium atom versus our potassium cation, the cation is going to be slightly smaller. So the yellow here would be the larger, the green would be smaller. Whereas if we take a look at the chloride anion, even though that this is an anion, which is going to be larger than the initial atom itself, it is so far over to the right on the periodic table that the atom itself is so small to start with. So since it is all the way over to the side, that means that the red atom will be our chloride anion. All right, so now we're going to discuss our formation of ionic compounds or ionic solids. So recall that an ionic bond is the electrostatic attraction between an anion and a cation involving a complete transfer of one or more electrons from one atom to another. And so these form an ionic compound, which is a neutral compound in which the total number of positive charges equals the total number of negative charges. And so this forms what's called a crystal lattice. So here we have sodium chloride, which is table salt. So we have sodium atoms and chloride atoms become ionized to form the sodium ion and the chloride anion. And those align in a very highly organized crystal lattice in order to form this ionic solid or ionic compound. So some of the properties of these ionic compounds are that they exhibit very high melting points. They're very hard and brittle. They have a low conductivity in their solid form. They're very highly soluble, but they exhibit a very high conductivity in their solid form. So if you think about your typical table salt, that really exhibits all of these different properties. Okay, it's very difficult to melt table salt. They're very hard and brittle. If you hook up to a solid crystal of table salt, it's not conductive, but it's very highly soluble. And if you dissolve that in water, it is highly conductive. So if we think about forming all of these different all of these different ionic solids, we can create what's called a chemical formula for each of these ionic compounds. And so, as we mentioned previously, you have the combination in a very fixed ratio in order to obtain an electrically neutral species. So if we take a look at each of these different compounds given to you, we need to find a way in which each of them are going to arrange in order to form an electrically neutral compound. So first, if we take a look at sodium cation and chloride anion, both of these guys have a +1 and a -1 charge. So both of the charges are equal in magnitude to 1. So they would combine in equal ratios. For one sodium, you have one chloride. And that's it. That's simple. Moving on next to sodium, which is a +1 cation, and oxygen, which is a 2- anion. In order to create an electrically neutral molecule, we would have to have two of these sodium plus charges for every one oxygen, which carries a 2- charge. So the way we would write that we would have a sodium with a subscript of the 2, And then an oxygen, when there's no subscript here, that indicates that there's just um, one species present. So that means that there's two sodiums per every one oxygen. And so I didn't mention here, when you combine these guys together, we can drop the overall charges because they are now combined together into an ionic compound. Next, if we take a look at magnesium 2 plus and chloride 1 minus, so Mg2 plus Cl minus, we'll see here that we need to have two chlorides in order to counteract the 2 plus of the magnesium. And so what that means is for every Mg, we need two Cls. Okay, for the magnesium and oxygen, Mg2 plus O2 minus. So we can see now with a 1-to-1 ratio between these two, we actually have total balance. So we see for every one magnesium, it's balanced by one oxygen. And aluminum, Al3 plus, combining with a sulfide, S2 minus, we can see that we need to have two aluminums, gives us a +6 charge. If we have three sulfides, that gives us a 6 minus charge. So you have two aluminums and three sulfides. Okay, and so our last two that we can give us here are lithium and fluorine. So if we look on our periodic table, we see that lithium is one of our alkali metals. So that means that's going to have a charge of +1. And fluoride is a halogen, which means it's going to have a charge of 1 minus. So they combine in a 1-to-1 ratio, LiF. Okay, and strontium, we can see that strontium is one of our alkaline earth metals. And so that's going to have a charge of 2 plus. And we know that iodide is a halogen, so it'll be I minus, which means we have to have two of these iodines per every one strontium. So SrI2. Sorry for getting low there on the whiteboard. Okay, so we can see in all of these cases, we have a charge balance. So now I want to quickly show you a quick shortcut that you can take in all of these cases in order to determine how many of each are required. So if we take a look in each of these, when we combine these ions together, what you're going to do is you're going to take the magnitude of each of these charges, and then you're going to bring that number down as the subscript of how many of each atom that you need. So this is a +1, a -1. Bring them down, you have one sodium, one chloride. One sodium, or so a +1 goes down, tells you need one oxygen. 2 minus means we need two sodiums. So Na2O. Magnesium 2 plus turns into two chlorides. -1 for the chloride tells us one magnesium. So one magnesium, two chlorides. Really nice shortcut. Magnesium oxide, we have indicates we need two oxygens and two magnesiums. And if you have 2 and 2, you can reduce that down to 1 and 1. Okay, so if the same number applies here, you reduce it to its lowest common factor. Okay, aluminum 3 plus tells us we need three sulfides. 2 minus tells us we need two aluminum. Okay, so this is a really nice shortcut that can tell us how to very easily and straightforward determine the ionic compounds. So now that we have introduced the ionic compound, now we need to overview how to name these compounds. And so just kind of instinctively, I've been referring to these ionic compounds using their names. So hopefully you might have picked it up a little bit by just me discussing them, but the naming paradigm is really quite easy. So when you're talking about the metal cations, they retain their elemental name. So whereas sodium, that we call this a sodium atom, When we rip an electron away to make it into the sodium ion, we just simply call it a sodium ion. So instead of sodium atom, it's called sodium ion. That easy. When you rip electrons away from aluminum atoms, you get the aluminum ion. So the nonmetals then have a slight change in their name. They retain the root of the elemental name, but they end with IDE. So when you go from chlorine atom to add an electron to turn it into an ion, it now keeps the root, the chlor, but instead of INE, it ends with ide. So we call that the chloride ion. Oxygen keeps the root and turns into the oxide ion. Sulfur keeps its root and ends the IDE to form the sulfide ion. Okay, so that way you can know if I'm talking about oxygen, I'm talking about an atom. If I'm talking about oxide, I'm talking about an ion. So when we name a binary compound, which means just involving two separate elements, we combine these two ion names to read out what the ionic compound is. So if you combine the sodium ion with the sulfide ion, excuse me, you combine the two to form sodium sulfide. Okay, so now if we're taking a look at, and so for this naming thing, we're going to have a worksheet today that's going to work through a bunch of examples. So I'm moving on from that naming of binary, but you're going to get much more help with that, much more practice in these worksheets. So some of the transition metals form more than one type of cation. So if we take a look at some of these transition metals, we can see that vanadium, for example, can have a 2 plus or a 3 plus, chromium 2 plus, 3 plus. We can see all different sorts of ions that can be formed. So instead of being as straightforward as our alkali metals all form a plus 1, our alkaline earth metals all form a plus 2, we can have, it's not as clear cut when we're dealing with our transition metals. So transition metal cations that form more than one cation are written using the elemental name followed by Roman numerals denoting their charge. So for example, iron, when it turns into a 3 plus ion, is called the iron 3. Okay, and in that parenthesis, it's a Roman numeral. So Roman numerals again. So if we go up on the board, in case you're not familiar, 1 has Roman numeral of I, 2, II, 3, III, 4 is IV, 5 is V, etc., etc. Okay, and so the labeling for iron is we have this iron 1, 2, 3. Okay, so any of these transition metals here, it's a good idea to put their charge as Roman numerals in parentheses afterwards. So the copper 2 plus turns into copper 2. So how would you name the product of chromium with a 3 plus with I minus? So we indicate that chromium is one of these transition metals. So we're going to name him with his Roman numeral and call that chromium 3. And then iodine, when it forms into an ion, it's going to be called iodide. So that would form chromium 3 iodide. Okay, that'd be the name. So we're going to encounter other types of ions called polyatomic ions. So polyatomic ions are covalently bound groups of atoms that carry an overall charge. And so you never break up these polyatomic ions from their partners. So some of the examples of polyatomic ions that we'll encounter, the only polyatomic anion or cation that you'll find is called the ammonium ion. So that's a nitrogen in the middle and then 4 hydrogens around. And the overall ammonium ion carries a plus 1 charge. Okay, so that NH4 altogether has a plus 1 charge. Another example is the hydroxide ion. So a oxygen and a hydrogen combined together carry an overall minus 1 charge. A nitrate ion, a nitrogen, three oxygens. The whole thing carries a -1 charge. A sulfate ion, a sulfur, four oxygens. The whole thing carries a 2- charge. So these are polyatomic ions that stick together, that never are separated. So here's a list of some common polyatomic ions that you're going to encounter. And so all the ones that I have starred here are the ones that we're going to see on a regular basis. So these are all the ones that you want to make sure that you memorize. Okay, so take some time to sort of memorize these. And then we're going to go into now naming polyatomic ions. So for naming polyatomic ions, so you can, if we look back at the list, you can see there are several types of ions that look very similar to each other in name. So there, for example, is chlorate and chlorite, and their formula look very similar to each other, but there's a slight difference. Okay, for example, nitrate, nitrite. What's the relationship between all of these, and how do we memorize the names for these polyatomic ions? So my suggestion for that is to memorize the names and formulas for the common polyatomic ions. And so since most of these end in ATE or ITE, I recommend that we learn the ATE endings. Okay, so all the ones that end with 8. So that would be chlorate, nitrate, carbonate, chromate, sulfate, and phosphate. So if you memorize the formulas and the names that go with each one of these, then we can move on from there to determine how they are best named or how to adjust them for the different sort of endings. So let's go through and look at each one. So for chlorate, that's going to be ClO3 minus. Nitrate is going to be NO3 minus. Carbonate is going to be CO3 2 minus. Chromate is going to be CrO4 2 minus. Sulfate will be SO4 2 minus. And phosphate is PO4 3 minus. So you notice all of these polyatomic ions have an ATE ending. And so what I'm going to say is that these ATE endings are the most common form. And so from these ATE endings, we can now adjust them in order to get the other sort of endings that we find. So if we cut off the ATE and now end with an ITE ending, what that means is we have one less oxygen. Okay, so if we rip one of the oxygens away from each of these, it would go from nitrate, NO3 minus, to nitrite, which is NO2 minus. So one less oxygen is ITE. If you have a starting of hypo and then ending with ITE, that means two less oxygens. Okay, hypo means less, hyper means more. So hypoite means even less oxygen than ITE. Okay, if you have a prefix of so an example there would be hypochlorite. So hypochlorite would be two less oxygens. Okay, per as a prefix, and then ending with ATE, that means one more oxygen. Okay, so per ATE means more oxygen. So if we're talking about per chlorate, that means we're going to ClO4 minus. Okay, and the last one is if you have a prefix of the word hydrogen and then ends with ATE, what you're going to do is you're going to add an H plus, and that has the effect of reducing the overall negative charge by 1. Okay? So if we have hydrogen chlorate, we would add an H plus and we would remove one of the charges. Okay, so hydrogen sulfate, we would add an H and then we would reduce the negative charge from -2 to -1. And sometimes you'll see this hydrogen ATE also called bi as a prefix, then ATE. So bisulfate. So either one of these are interchangeable. Okay, so I would recommend starting with all of these ATE prefixes, or they're not prefixes, they're endings, ATE endings, and then remember how they are adjusted in order to best learn the naming. All right, so I ask you guys to write the chemical formula for the following anions. So I'd pause the video and work through those on your own after you've studied for a while. We'll go through them here together. So nitrite is NO2 minus. So you lost one oxygen. Perchlorate is ClO4 minus. We've added an oxygen. Hydrogen sulfate would be our HSO4 minus. So we've added the H plus and we've decreased the overall charge from a 2 minus to a 1 minus. Chloride, this is just simply our Cl minus. Okay, it's not, remember the IDE ending does not indicate that it is a polyatomic ion. It's just our chloride ion. And then finally, hypochlorite. That's going to be ClO minus. And so that's a removal of 2 oxygens. Okay, so if we are now naming the ionic compounds involved in polyatomic anions, it's really easy. We do it the exact same way that we did previously, in which we start off with the name of our metal cation, and we just follow it up with that name of our polyatomic anion. Okay, so if we're mixing magnesium, the magnesium ion, with sulfate, you just combine the two together to form magnesium sulfate. Okay, so from there, I will break you guys off. There are 2 separate worksheets that you should complete for this activity. And then so it'll go through a bit of practicing and recognizing polyatomic ions and naming binary and polyatomic ionic compounds. So with that, we're finished for the day. Thank you.